So we're going to work on the second half of lesson 9.1, which was on geometric means today. We're going to look at a little bit more insight into, how those, when you put an altitude into a right triangle, how you actually create three similar triangles. And then we're going to look today at how those similar triangles give us the geometric means concepts we looked at yesterday. And we're also going to do some application of some geometric mean questions. So first of all, here's what we worked on yesterday. QSR is our right triangle. S to T is our altitude that we put in. And then yesterday we worked on a couple of theorems that talked about how of this original right triangle, this QSR, we can add the altitude and then find missing side lengths of QSR. Well, before we get into a little bit more talk on that, I want to talk about how, or at least, and identify how the three right triangles that are now created are similar. Okay, so when we put this altitude in, you're going to have three similar triangles. So I just want to kind of point those out first. So here's our first one. It's this TRS triangle, and I kind of rotated it so it looks like this down over here. A second triangle would be STQ. And then our third triangle is actually the original one we started with, which was QSR. Now I've oriented them all so that they all are laying in the same position. And what we know is that these three triangles taken from this drawing are all similar to each other. Similar meaning same size, or excuse me, same shape, different size. The reason they're similar is by the angle postulate. Notice they all have a right angle, so they all have a 90 in common. The middle and the last one share angle Q and a 90, so they're similar. These two triangles are the first and the last, I just say, share angle R and a 90, so those two are similar. And then using the transitive property, all three of these are similar to each other. So we know that STR, QTS, and QSR, all these triangles are similar. So that means they're all made up of the same angles, and therefore that their sides are all proportional. And that's where this whole geometric mean concept comes from. So what I want to show you is let's go back to our original triangle here. If we wanted to find the distance of SR, the length of SR, what we learned yesterday from our theorem was the length of SR is equal to the length of QR times TR. Is the square root of that, I should say. Now let me show you where that comes from. Let's come down here and kind of eliminate the middle triangle and look at these two on the outside. Notice that both of these triangles have SR in them. In this case, SR is our hypotenuse, and over here, SR is a side length. Now, these two triangles are proportional, so I could say this hypotenuse SR, the ratio of that hypotenuse SR to the hypotenuse QR, is equal to this leg RT to this leg RS. Now, if I write that out, it looks like this: SR to QR, RT to SR. Notice that I have SR in both of my positions of my proportion. If I do cross products and solve, SR is the geometric mean, or it is the square root of QR times TR. So that's where our geometric means concepts come from. They actually come from these similar triangles in here. All right, let's say we're trying to find QS. Okay, we learned yesterday in the theorem that QS would be equal to the square root of QR times QT. Now let's look at where that came from. Let's now eliminate the small triangle and let's look at this one. Remember, we're trying to find QS. So QS, which is the hypotenuse of this triangle, and QS, which is the side length of this triangle, that's the same segment. So again, these triangles are proportional. So I could say the ratio of QS to QR, okay, is equal to the ratio of QT to QS. Now I've written a proportion that has QS in it in both of the ratios. If I do cross products and simplify, QS is equal to QR times QT. That's that theorem from yesterday. And then finally, if I wanted to look at finding ST, which is that the altitude that I put in, I'm going to look at the small two triangles. Now, again, I want to write ratios that involve ST. So I'm going to say ST to QT I'm going to say RT to ST in my ratio. So ST to QT, RT to ST. Again, where the sides are proportional, cross products, and that gives us the altitude is equal to the square root of these two segments, QT to TR. Okay, so that's just kind of an insight into where those geometric ratios came from yesterday, and how the rules came about. It's the same rules. I just showed you where the triangles come from to do that. Okay, so tonight this is going to be a question that you get. Write a similarity statement identifying the three triangles in here that are similar. And remember, when we write the similarity statement, we have to have the vertices matching up. So I have to write it in a special way so that everything matches up correctly. In this case, triangle, if you look at KML, M is the right angle here, KML, KPM, that's the right angle, and then MPL, that would match up the corresponding sides correctly. Now, some of the questions I know tonight are going to give you triangles like this and then specifically ask you to name them in the correct order. Others are going to say, what is what other triangle would be considered similar to this one? So they're all the same style of question, but you'll see when you're doing the homework tonight that they're going to ask this question a few different ways. But essentially, you got to match up those corresponding angles in the similar triangles, and it may help to redraw it like I did for you on the last page. Okay, the last concept for today is going to be us to use geometric mean to solve an application problem. So what that's going to entail is us using those two theorems that we worked on yesterday, either finding a side length of a right triangle or finding the altitude of the right triangle. So in this case, Diego was trying to find the height of this bike ramp. So we're looking for the whole height here. Okay. It says he's 6 foot away and he's lining it up, this book, so that the top and the bottom of the ramp are just in view of the book. And since the book's a 90, this is a 90. So that's creating our right triangle. He's 6 feet away. They're asking us to find X. Okay. It's also telling us this 5.5 is coming from his height here, his eye level. So that's where the 5.5 is coming from, and he's 6 foot away. So what happens here is this 6 foot distance is representing the altitude of this right triangle. So what we're going to know is that this 6 foot is equal to the product of these two square roots. So it's the square root of 5.5 times X. Now, this is a little different for us because X is under the square root symbol. So we're going to have to solve to get X in this case. So our equation solving processes are, if something has a square root symbol around it, we can cancel it out by squaring it. Squares and square roots are inverse operations. So we're going to square both sides of the equation. Okay. It's going to give us 36 equals, and then the square cancels the square root. So what's left underneath is what we're going to have, 5.5x. Divide each side by 5.5, and you get about 6.5 as our result here. So X is 6.5. You guys have heard me say many times, multiple choice test. This will be choice A. However, how tall is the ramp to the nearest foot? So the ramp is actually going to be the 5.5 plus what we just found, 6.5, to get us to 12 feet. So make sure we answer the question completely. This is one style of application. Okay, another style. So this is like a cutaway view of a roof line. ZYX is our right triangle. Y to W is our altitude that's been dropped in. They're asking us to find this altitude height. Okay. Now here's the thing about the altitude height. The altitude height is the square root of ZW times WX. We know that Z to X is 6.3, but we don't know the breakdown of what these two are individually. So we're going to have to do a little extra work to find that. So what we're going to do is we're going to use this side length, this 5.5, and the fact that Z to X is 6.3 to find ZW. Let me show you what I mean. We're going to find ZW first. So I'm going to do the side length theorem here. I'm going to say that YZ is equal to the square root of ZX times ZW. Now, when I substitute in my values, the only unknown is ZW. I know that YZ is 5.5. I know the full length across Z to X is 6.3. So I'll be able to find ZW by solving this, similar to what we just did. We're going to square both sides. We're going to divide by 6.3, and we get ZW to be about 4.8. So Z to W is 4.8. Now, to find H, I got to know ZW and WX. Well, we can find WX because we know that ZX is made up of ZW plus WX, those two added together as segment addition postulate. So we know Z to X is 6.3. We know Z to W is 4.8. So that leaves WX to be 1.5. So now that I know my ZW length and my WX length, I can find this H, which is YW, it's the altitude, by using my altitude theorem, which says that the altitude is equal to the geometric mean of these two segments it's divided this overall hypotenuse into. So it's going to be 4.8 times 1.5, square root of that product, which is a square root of about 7.2, which is about 2.7. So we now know the height of this triangle, if you will, or the altitude of this triangle is going to be 2.7 meters. So that's a different style of application. You're going to get one or the other in tonight's homework. So tonight's work is to get on the McGraw-Hill site. And I think I got 10 or 11 questions that are involving the concept of either, matching up the three different congruent types of right triangles, inside a right triangle, which an altitude's been drawn, and also doing some application questions.